Acquiring and analyzing samples from beneath the surface of an extraterrestrial body provides valuable information about its composition and cross-section. Subsurface samples could, for example, reveal the presence of water beneath the surface of an extraterrestrial planet or moon. Sample acquisition is the first step in analyzing soil and conducting experiments with rocks. The robotic planetary rovers, which carry out these missions, are built with the intention of bringing scientific instruments to locations of interest. There, the acquired samples are used for in situ analysis, or they are being collected for transport back to Earth. Acquiring soil samples requires a general knowledge of the chosen environment to ensure that the right kind of tools are available. Next to icy regolith, there are two types of non-icy regolith to differentiate between. There's regolith on bodies with an atmosphere, which is subjected to weathering but spare microtectite bombardment. An example for this would be Mars. On the other hand, there is regolith that is on bodies without an atmosphere and therefore not subjected to weathering, but has to deal with microtectite bombardment, like the regolith on the Moon. Several different methods to acquire the soil samples exist. These include sample acquisition by robotic manipulator, abrasion, corer, burrowing, and drilling. Robotic drilling is a prerequisite when analysis of subsurface samples from a certain depth is desired. The following will only concentrate on sample acquisition by a subsurface drill. To ensure a successful mission, many considerations have to be taken into account before, during, and after the drilling occurs. When the mission is being planned, specific goals are established. Various characteristics like the drilling site, the drilling depth, the drill design, and the method of drilling are derived from the mission goals. The actual drilling is a sequence of 3 steps. These are the penetration or drilling into the ground, followed by the removal of the cuttings and extraction of the sample, and lastly the maintenance of the borehole integrity. A ground-penetrating radar, among other sensors, can be used to detect in advance which drilling sites are promising for a specific mission. If, for example, the mission goal is to detect subsurface water, the ground-penetrating radar can be augmented by electromagnetic sensors, thus heightening the chance to actually acquire samples with scientific value to the mission, even before the drilling begins. This leads to surface mobility of the rover being an equally important factor as the drilling infrastructure itself. The classification of a planetary subsurface drilling mission is generally carried out according to the drilling depth that is desired to be reached. The differentiation ensues between near-surface drilling, shallow depth drilling, and deep drilling. When considering near-surface drilling, depths between 5 to 10 centimeters are looked upon. This usually does not raise any difficulties. For shallow depth drilling, the depths of about 200 meters are technically possible, although this comes with great challenges regarding the necessary infrastructure. Additionally, the need for human presence may not be avoidable. The search for liquid water, for example on Mars, calls for what is classified as deep drilling. This includes depths down to more than 5 kilometers. Drilling this deep is currently not feasible on extraterrestrial bodies. For scale, on Earth, depths of about 12 kilometers are manageable. However, This assumes human interference and complex infrastructures. Generally speaking, the use of subsurface drills is viable for depths beyond 1 meter. This is because samples from above 1 meter are expected to not deliver different scientific findings than what is possible with robotic manipulators or other shallow acquisition techniques. Concerning the scientific value that subsurface samples possess and the technical restraints for drilling, the depth range between 5 to 10 meters is thought of to be the most interesting. The drill is designed with the primary goal to enable it to take soil samples from beneath the surface of an extraterrestrial body. As human presence is not given, the drill has to be able to work fully autonomously. Since the subsurface composition and the drilling medium varies with the drilling site and also the drilling depth, the drill needs to be able to handle rocks of differing composition and hardness. Drilling mediums may include icy soils, sedimentary rock, sandy soil, or volcanic rock. Steel is a common material used for drills. A more lightweight alternative is represented by titanium alloy. Another possibility for the drill bit design are diamond-impregnated bits. They are made out of a soft metal, like bronze, and have small diamonds scattered in them. As the soft metal slowly wears off, the small diamonds are uncovered and drilled into the rock. Fresh cutting teeth will be exposed as the drill wears off. Overall, the drill and its surrounding infrastructure must be of low weight due to the problem of transporting the drill to an extraterrestrial body. Additionally, it must work at lower power levels than compared to on Earth because power might be a scarce resource. When attaching the drill to the rover, it is imperative to not limit the rover's locomotion capabilities or to interfere with other rover systems. To cope with bit jamming, the drill needs to be jettisonable, otherwise the whole rover is in danger of being stuck. Furthermore, a good balance needs to be found between compact design with short drill segments that can easily be stowed away and reduction of critical breaking points. The drill string is more vulnerable as it gets longer and consists of more separate segments. Irrespective of the method that is used for the actual drilling, an important consideration deals with the removing of the cuttings from the borehole. Different techniques exist to remove the cuttings. Generally, it is possible to use a continuous flight auger or a screw conveyor, a cyclic lift auger, gas circulation, or liquid mud circulation. The most commonly used method is to use a continuous flight auger to spiral out the cuttings out of the drilled hole. Using an auger to transport the cuttings limits the mission to depths of about 10 meters, as the power consumption rapidly increases for deeper holes. A disadvantage of employing an auger is that it struggles in contact with wet or sticky materials. Instead, a mole may be utilized to pump circulating liquid xenon or carbon dioxide from the surface to subterranean levels. The xenon or carbon dioxide is transported in thin tubes connected to the mole and ejected underground. It then mixes with the soil or ice samples and transports the samples back to the surface, similar to drilling fluids on Earth. An advantage of carrying out this process with carbon dioxide as a medium is that for planets similar to Mars, carbon dioxide can be won out of the atmosphere. This would, however, call for a compressor on the surface of the planet. A positive side effect of the cuttings removal process is that it reduces overheating, as it also removes about 70% of the heat that is created during the fracturing of the rock. Borehole integrity deals with the problem of keeping the drilled hole from collapsing in itself. This is especially critical in sandy sediments. To maintain the integrity of the borehole, one method is to install some kind of piping along the walls of the hole. These pipes are usually made out of metal or plastic and are also called casing. Different drilling methods exist. Each approach handles challenges in distinct ways and offers various advantages. This renders a broad spectrum of techniques to choose from for specific mission requirements. Rotary drilling is considered to be a more traditional form of drilling, as it is a commonly used method, both in existing space missions and here on Earth. The petroleum industry on Earth offers a fundamental level of experience that can be used to design space missions with rotary drilling applications. Rotary drilling involves a drill bit that is rotated and pushed into the ground. Thrust and torque are exerted simultaneously. A disadvantage of rotary drilling in general emerges regarding the drilling depth. For depths deeper than about 1 meter, it becomes challenging to provide a fitting infrastructure for the drill. For deeper depths than about 1 meter, it will be necessary to autonomously assemble the drill string in the extraterrestrial setting. It is possible to assemble the drill string while the drilling is in progress. As the drill advances deeper into the body, individual drill segments are attached to the continuous drill pipe. When extracting subsurface samples through this method, the morphology of the rock samples will not be changed through possible contaminants from the surface during the drilling process. However, mineralogical changes in the rock samples may occur due to the high temperatures of about 250 degrees to 500 degrees that are locally reached as the drilling takes place. Furthermore, gouge and shear effects on the rock have to be looked upon when extracting subsurface samples by rotary drilling methods. When considering rotary drilling for a space mission, it is important to also regard several other factors. The drill bit is dealt with every use and has the capability to break in the worst-case scenario. Further, the initiation as well as the whole process of the drilling demands a substantial amount of power that is not trivially accumulated on an extraterrestrial body. The axial forces that are applied are very high. In addition to that, single-point failure modes are not to be neglected. The rotating and moving parts of the drill string are thereby particularly endangered. There is a potential for drill walk and bit jamming. Lastly, even though support structures above the surface may be kept relatively small in comparison to terrestrial drilling sites, they are not completely indispensable. In comparison to rotary drilling, percussive drilling is more efficient. Percussive drilling makes use of kinetic energy to reach subsurface levels. This method works through the hammer and chisel principle, where stress pulses break down the sediment into smaller fragments. During the process of percussive drilling, the rock is chipped and crushed. This method is especially suited for hard, brittle sediments. The drill blows on the rock continuously. However, with each new impact, the bit is slightly rotated and a new point on the rock is being drilled. The impact frequency for percussive drilling usually lies between 20 Hz to 60 Hz. Percussive drilling becomes energy inefficient for depths deeper than 10 meters because of dissipation effects in the drill column. Deeper levels may be reached by combining percussive elements with rotary drilling. To realize this, the rotary drills are modified by attaching downhole hammers. The tool will be raised and then dropped for about 1 to 2 meters to break the sediment. One type of percussive drilling is ultrasonic drilling. This method is fast and does not suffer from drill bit dulling. However, the power consumption for ultrasonic drilling is very high, as is the energy dissipation when drilling softer rock. An overall advantage of percussive drilling lies in the fact that it does not need drilling fluid during the process. Drilling fluids may be used in rotary drilling methods to cool down the bit and to bring cuttings out of the borehole. Additionally, percussive drilling is not limited by complicated drill string assembly for deeper boreholes. On the other hand, this method is associated with a low rate of penetration when it comes to harder rocks. Another problem arises when considering how to transport the chiseled rock out of the borehole. Lastly, core sample integrity is not assured for percussive drilling. The term non-traditional drilling comprises, among others, methods that use laser beams, electron beams, or microwave jets to reach the subsurface of a body. These methods to gain samples are generally associated with a high resource consumption. For example, the power that has to be accumulated is about 3 to 5 times higher than that in traditional methods. The power which is used is typically a rare resource on extraterrestrial bodies. Therefore, these forms of drilling are marked with a non-negligible disadvantage. Other novel drilling methods are inspired by nature. The wood wasp Syrinx noctilio has an ovipositor that can drill into the bark of trees, where the wasp then lays its eggs. The proposed method for a planetary drill, inspired by the wood wasp, is called a biomimetic drill. The ovipositor is made out of 2 sections that operate reciprocally and are equipped with teeth on the outside. The teeth alternately deliver the force that is needed for drilling the other side deeper into the material. These teeth then, in turn, become volumes on one side of the ovipositor and transport the waste out of the hole. The Rosetta mission included a payload for coring and sampling the soil of a comet. To acquire the samples of interest, the SD2 sampling drill was used. It is a rotary drill. Its goal was to retrieve ice samples from beneath the surface in varying depths of up to 0.25 meters. The drill itself is 12 millimeters in diameter and consists of a helical auger and polycrystalline diamond cutters on its head to drill into the icy soil. Based on the Rosetta SD2 drill, a different drill called the D3 evolved for simultaneous drilling and core sampling. The novel approach of the drill is that the drill and the sampler are the same device. The drill is a steel rod and it has a central sliding piston in the middle of it that opens up a volume and serves as the sample container. The ExoMars mission also makes use of a subsurface drill that is in turn based on the D3. The depth requirements for this drill were set to 2 meters below the ground, where it will recover rock samples. The drill diameter is 25 millimeters. The soil samples will be 40 millimeters in length and 10 millimeters in diameter. To reach the designated depth of 2 meters, 3 extension rods of 575 millimeters have to be assembled onto the drill to form a string that is long enough to reach 2 meters below the ground. only the first rod has a volume to retrieve the samples. When the first rod is fully underground, it disconnects from the mandrel and the next extension rod is placed in between. After the samples are acquired, the drill string is lifted out of the ground and disassembled. To summarize, many considerations have to be taken into account when planning a mission to retrieve samples on extraterrestrial bodies through subsurface drilling. Since the environments on the bodies of interest can vary extremely, there is not one method that satisfies all missions. As of now, 2 methods are estimated especially appropriate for the use on extraterrestrial planets. These are rotary drilling and percussive drilling. Generally, planetary drills are most often rotary drills that use a helical auger. Although this is not the most efficient method regarding power efficiency, and in spite of problems posed by bit dulling and autonomous drill string assembly, this method is favored because of the substantial amount of knowledge and experience connected to it. This poses problems as on Mars, rotary drills are not assessed to be the most reliable option. The Martian planet's overall dusty regolith poses as a potential threat to the rotating parts of the drill. Furthermore, the dust also makes the autonomous drill string assembly hard if certain depths are to be reached. A major point of concern when it comes to the reliability of the drilling method in general is the need for autonomous assembly of the drill string. This problem may be evaded if there is no drill string that needs to be assembled. Percussive methods may be a solution. Regarding the drilling depth and near-term missions, it is not expected that depths below 5 meters will be realized, as the technology deployed on extraterrestrial planets is not yet as advanced.